Thank you. Thanks. So we learned how to, like, the basics of what a confidence interval is. Now we're actually going to learn how to find it using this lovely formula right here. That'll be your new friend. All right, so why do we do this? Here are some examples. If we want to find an unknown population parameter, like what proportion of U.S. adults are unemployed right now, or what proportion of high school students have cheated on a test, or what proportion of pine trees in a national park are infested with beetles? We might need to know. All right. Yeah. So activity. We're not doing this. We should have done this yesterday. But I didn't do it. All right. So we've got a bag of beads, okay, and you're trying to find the number of red beads in the whole entire container. So imagine a large container of a lot of different beads. You guys are going to take a simple random sample, okay? So you're going to decide how you want to do that. You're going to maybe dip a cup in, grab a bunch of beads, and you're going to count how many are red. So we're using a sample proportion of how many are red. Point estimate would be what we got, right? Our point estimate would be we got like 100 red beads out of 300 beads or something like that, okay? And then you guys would guess on how to do this, but I'm just going to tell you how. So, all right. First, you have to have these conditions. We talked about this yesterday in your notes. So remember, I called the wrong thing. But anyways, so you have to have random sample. You have to have the 10% rule so you can do standard deviation. And you have to have large counts, which that's what I called the wrong thing, but that would be NP greater than or equal to 10, except now we're going to use P hat because we don't know the true P. And N times 1 minus P greater than or equal to 10. By the way, these are for P's, right? Everything we're doing right now is proportions. What was the rule when we were doing X bar, the mean, the sample mean? Greater than 30, okay? So this is the rule when you're doing proportions for large counts. If we're doing the means, you got to do greater than 30. All right, 10% condition, though, this is the same for either of them. Our sample has to be less than or equal to 1/10 of our population. All right, so those have to be true. When Mr. Vignilione's class did the beads activity, we'll say Mr. V, they got 107 red beads and 144 white beads. Their point estimate for the unknown proportion P of red beads in the population is what? What should we put for our point estimate, you guys? P hat is equal to what? Thanks. Your total, right? 107 over the total. So we have to add this many red, this many white. That's how we get our denominator. So what decimal is that? 0.4. Thanks. Someone who has their book open. That's helping me out. Thank you. We did this in the wrong order. Not very helpful. Cool. All right. So that's called our point estimate, and then we're going to be adding and subtracting a certain amount so that we can construct a confidence interval for what's in the actual container, the whole thing. All right, so Mr. V's class wants to construct a confidence interval for the true proportion of P of red beads in the container. Recall the class sample has 107 red beads, 144 white beads, so we just did our P hat. Check the conditions. So before we actually do the confidence interval, we have to check the conditions. So don't just put random check, okay, 10% check, right? You got to, like, say something about it. Yes, stats has a little bit of writing. So let's see, random. What did it say that we did, you guys? What did we do when we did our random sample? How did we get our sample? Well, we took a random sample of 251 beads, so we know we did a random sample, right? We didn't just pull out the red beads. We mixed it all up, and we dug in there and grabbed 251 beads. So, is it random? Yes, because the class took simple random sample of, they do and for S, NSRS, just in case you're wondering, of 251 beads from the container. So write a short sentence to say why it's random or not random. It's not, okay? And then we're going to check the 10% condition. So how many beads, what was our N? How many did we pull out of the bag? Thank you, 251. That has to be less than a tenth of the total. And Mr. V told me that there were 3,000 beads in the container. So good news, we're less than or equal to 300, which is a tenth of the total. All right? Yay, 10% condition works. And then we have to check large counts. All right, so this is interesting, and you guys should pay attention on this large counts. So this is where we do n p hat greater than or equal to 10, and n1 minus p hat greater than or equal to 10. What's n? 251, okay, so we drew 251. What's our sample proportion that we got? 107 over 251. What is going to happen every time on these? Every time we do these with proportions. So really, you only have to check that 107, how many you got that were red, is greater than 10 because those cancel out. And we have to check the 1 minus, right? So this would be 251 times however many were not red. Wasn't that 144? So we had 144 that were not red. Okay, so greater than or equal to 10. So really we can check 107 and 144. As long as those are greater than or equal to 10, it's the same thing as our NP, all right? But if you're going to forget, then make sure you do the NP so you don't forget how to do it. Okay, so yay, can we construct a confidence interval for the bead problem? Yes, we can, because we have random 10% and large counts. So if one of the conditions is violated, you guys, it's not going to give us a good estimate. So for example, if we have a poorly designed experiment, like we did a convenience sample, then there's no point in constructing a confidence interval. Okay? I feel like we're probably good on these, but let's run through it. So in AP Stats class, we conducted a survey, and they asked the first 100 students to arrive at school one morning whether or not they slept at least 8 hours the night before. Only 17 said yes. David S., do we have a random sample? No. What kind of sample is that? That would be like a convenience sample. We're asking the first 100 students if they got enough sleep. All right, so no. We still want to check the rest of them. 10%. 100 students, do you guys think that's less than or equal to 10% of the total population? Yeah, probably, if it's a large high school. That's what it says, okay? And how about large counts? We got 17 that said yes. So how many did not say yes? 83. So 17 greater than or equal to 10? Yep. 83 greater than or equal to 10? Yep. Okay, so number 2, a quality control inspector takes a random sample of 25 bags of potato chips from the thousands of bags filled in an hour. Of the bags selected, 3 had too much salt. Maddie, did we take a simple random sample? Yes, so we're good to go on random. 10%. Michaela is 25 less than or equal to a tenth of the thousands of bags. Yes, so we're good on that. And then we have to do large counts. So we got 3 bags with too much salt out of our 25. So how many did not have too much salt? 22. So 3 and 22 have to be greater than or equal to 10. Uh-oh. 3 is not greater than or equal to 10. So do we have large counts? No. All right. Cool. So let's construct a confidence interval. When the conditions are met, the sampling distribution for P will be approximately normal. And this is our same thing we learned before. You don't need to write those down. Okay, approximately normal, where our mu is the true mean. Okay, our standard deviation is that lovely formula. So we always, when we do standard deviation, have to check the 10% condition, right? But now we don't know the true p, and so we replace it with p hat. So we no longer call it standard deviation, we call it standard error. It means similar thing, all right? We just call it standard error because we're using p hat. This is what we will add or subtract, well, with another number in front of that. But anyways, you might want to write this formula down. So SE stands for standard error, and this is when we're doing proportions. So we use this formula. Again, same formula as before, but with p hat. So what's the definition of standard error? When the standard deviation of a statistic is estimated from data, the result is called the standard error. Okay, so we're estimating the standard deviation, and so it's called the standard error. Okay, so remember our general formula for a confidence interval was the statistic plus or minus the critical value times the standard deviation. So now we know how to find the statistic, that's your like p hat, and we know how to find the standard deviation using standard error, all right? And then we need to figure out what the critical value is. So this is our formula that we're going to use, which comes from that same generic formula. So p hat is the statistic, okay, plus or minus the z number right here, this little z star is our critical value, which we're going to talk about, and times the standard deviation formula. So this formula is really important, and you want to make sure you know it. Another thing I would most definitely write down is what this is actually called. So this is called a one-sample Z interval for a population proportion. We're going to have a whole bunch of different kinds of intervals by the end of this class. This is the first one. So we have one sample. We're using normality, so Z's. We're finding an interval from a population proportion, since we're doing P's. When the conditions are met, a C% confidence interval for the unknown proportion P is this lovely formula. Z star is the critical value for the standard normal curve with C% of its area between negative Z and Z. We are going to find Z scores based on that 95% or 90% or 80% or however confident we want to be. All right, it's not as hard as it looks. It's actually really easy. So how do we get critical values? As long as the large counts condition is met, we can use the normal curve, right? If we don't have large counts, we don't have normality. So we did check for large counts, which means we can use the Z score. You can use inverse norm or table A, whatever you prefer. I'm guessing it's inverse norm. So let's say I want to do 95%, right? I want to be 95% confident. Well, I need to find the numbers on that Z-score right there that leaves out the 5%, okay? So if I'm 95% confident, we're 5% where it's not. And that means the area on each side, and this is important, if I'm 5% away, what's the area on each side? 2.5%, or if you can't read that, 0.025. That's the same thing, right? On each side. So what's my critical value for 95%? I want to find the area here to here. That'll give me a Z-score. So we go to our calculators, and we go to menu. You guys might want to grab a calculator if you don't have one. There you go. All right, so menu, statistics. What did we always go to for these? Distributions, right? Yeah, inverse norm. Got nervous there. All right, inverse norm. So our area for 95% is always 5% divided by 2, okay? Every time you're doing the same type thing. So 5% divided by 2. So our area is 0.025, and we're finding a z-score, so you're leaving it 0 and 1, because that's the normal curve. Press OK, and we get negative 1.96. It will be the same z number every time, okay? Right, for 95%, it will always be this. So eventually you'll kind of have these down, but if you forget them, you can always plug it in, which is what you should do. The negative doesn't matter because it's positive and negative on either side, plus the formula is plus minus. So what am I going to plug in for z? 1.96, or for z star in our formula. That number will be 1.56 when we're doing 95%, right? So what about 99%? So that means I'm going to take 1% and divide by 2. What decimal is that? Yeah, so go back to menu, statistics, distributions, inverse norm. 0.01, right, is 1%. So it'd be 0.005. A lot of people do that one wrong, so make sure you do that right. 0.005. All right, okay. Negative 2.58, or 2.58, since we don't use a negative. There's our z-score. And 90%, you guys try it. What would you put in for the area? You take 10% and you divide by 2. So what goes in? 0.05. What'd you guys get for your z-score? Okay, 1.64. Cool. So that's how you find the little z value that goes in the formula. So now let's actually do one with Mr. B's class and the bead activity. Let's find a confidence interval that makes sense. It's the other percent divided by 2. Yeah, so if it's 90, you do 10% divided by 2. If it's 95, you do 5% divided by 2. Okay? All right, so we're going to do a 90% confidence interval for P. So for part A of this is our bead activity. We are going to use the formula. All right, so let's plug in. So P hat, you guys, P hat is what our statistic was. We got 107 over the total. What was the total again? All right, so 107 over 251, or just plug in that decimal. Plus or minus our z-score. Well, 90% confident. Again, we take the 10% and we divide it by 2, and we do our inverse norm to get that z-score, or use your table. And what z-score did we get for 90%? 1.64. Cool. And then we're going to plug in P hat. What is this decimal again? Somebody thinks. Who has this? 0.426. And then this would be 1 minus 0.426. And in the denominator is n, and that would be our total number from our sample, which is 251 beads. Okay? So I'd start with this. I would multiply by 1.64. Someone tell me just what decimal you get before the plus or minus. You could, I guess, plug that whole thing in. All right. Because we would get 0.426 plus or minus 0.061. You guys agree with me? Okay. Okay. So this number right here is our point estimate, just in case you forgot. And this number right here is our margin of error. And we write that as an interval. So we add and we subtract. So the left-hand side should definitely be the smaller one. And the right-hand side we add. So we get 0.375 and 0.477. And what should we always do after this? We should probably interpret that. So that's that lovely sentence that you guys memorized or are working on memorizing, right? So you would say, I'm not going to write all this out, we're 90% confident that the interval from 0.375 to 0.477 captures the true proportion of red beads in Mr. V's container. Okay? So we're 90% confident that from here to here is the true proportion. Well, what if part B, Mr. V claims that exactly half the beads in the container are red? What if he says half the beads are red? Would you guys believe Mr. V? No. Do we have a plausible evidence here to say he's wrong? Yeah. We don't know, but you could say because 0.5 is not in that interval, we have good reason to doubt Mr. V's claim. Make sense? If it was in the interval, you could say, all right, his claim is probably true. We're not doing this. It'll take forever, but we are going to do one where we put it all together. Write down this lovely 4-step thing. I know, I'm sorry. We got to go through every step at least once, though. Steps. So when you guys are doing the like frappies and free response questions, you're going to want to follow this lovely process every time. Every time. So we're going to state what parameter do you want to estimate and at what confidence level. So I want to find the true number of red beads at a 90% confidence level or whatever. Okay, you got to state that. Plan. For plan, you guys have to state what you're using. For example, this is the only one we know so far. We're going to use a 1-sample Z interval. Okay, so the plan is what you're using. This is a 1-sample Z interval. And then you have to go in your plan step and do, is it random, 10%, and large counts. So your plan step includes, does it meet the conditions that we need to meet? Okay, do is the calculations part, which means plugging into the formula. So that's easy, okay? And then conclude is write your sentence to conclude. All right? State, plan, do, conclude. Okay, here we go. Teens say sex can wait. You guys ready for this? All right.
This is too much.
It's a little too much for me, too. All right. Here we go. The Gallup Youth Survey asked a random sample of 439 U.S. teens aged 13 to 17 whether they thought 13's a little young, but yeah, whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes. Construct and interpret a 95% confidence interval for the portion of teens who would say yes to this question. Got to keep it interesting. All right. Oh, I guess I accidentally wrote down the state part for you guys. So there's the state part. So here's what you want to state. We want to estimate the true proportion P of all 13 to 17-year-olds in the U.S. who would say that young people should wait to have sex until they get married with 95% confidence. So state what you're trying to find and make sure you're doing your confidence level, okay? That's your state. You guys are just watching this. All right, plan. For the plan part, again, we have to say we should use a 1-sample Z interval if conditions are met. So this is where you guys need to memorize that, a 1-sample Z interval, as long as we have those 3 things. So, random. Jake, is it random? Oh, you're doing all of them for me. Hold on. 10%. I'm not convinced. Tell me why 10% works. Tell me what you're plugging in here. Yeah. Okay, good. So he multiplied by 10. Everyone good with that? That's a good way to do it. And large counts. N times P Greater than or equal to, again, you can cross off, right? So what number am I actually looking at for this? 246 has to be greater than or equal to 10. And we got to subtract 439 minus 246, which is 193. So do we have large counts? Do we have normality, basically? Yes. All right, so there's our plan. And now, of course, we're going to do this. P plus or minus the z-score starred. Just kidding. Ooh, that's really bad. Just writing that formula real good. All right. So, P hat. P hat. Charlie, what's P hat going to be in this problem? No, that's what we do for the z-score part. But P hat's got to be our actual proportion in the sample. Yeah, 246 over 439, which we will reduce here, plus or minus. All right, to get that z value, that's where we look at the 95% inverse norm. And Tyler, what would you plug into your calculator for 95%? Good. 0.025, right? So 5% divided by 2, 0.025. And did anybody write that lovely number down? Or if someone would calculate it, what is it? It's the same every time. Ginger, what is it? Thank you, 1.96. All right, 1.96, and then we've got P hat, that's this number here, so that's 0.56. Okay. And then 1 minus 0.56 is 0.44. Divided by n, that's our 439, our total number in the sample. Okay, plug those in, add and subtract, and we get 0.514 and 0.606. And the last part is make sure you write a conclusion. And so anyone think they can do that lovely sentence for me? Let's see, Chelsea, what do you think? We are, start with that. Interval. Yep. Right there? Yeah. Who say they will wait to have sex. All right. We are good. All right, here we go. Remember the margin of error includes sampling variability. Okay, don't forget there are other sources of error that are not taken into account. So for example, in this one, we're assuming that these teens answered truthfully. If they didn't, our estimate would be biased. Okay. Other problems like non-response or the wording of the question can also affect it. So just so you know, sampling beads is a lot easier than sampling people. Yep. AP tip exam. So just so you know, don't forget, or exam tip, yep. Make sure you do the 4-step process. Do you guys want to learn how to do this on your calculator? Yes. It's easy with the formula. Now, I am going to check that you plugged in the formula, and the book doesn't show you how to plug it in, so make sure you do it. Do you want to learn this tomorrow, or? I feel like it's not that big of a deal, yeah.